Every 26 seconds, with almost no variation, the ground beneath your feet moves. Not in a way you can feel, not in a way that registers on any instrument designed for ordinary vibration, but on the most sensitive seismographs on the planet, instruments capable of detecting the slow grinding of tectonic plates, the faint echo of earthquakes on the other side of the world. This signal appears, clean, rhythmic, relentless. The popular version of this story goes like this. Earth has a heartbeat. Every 26 seconds, something pulses. Nobody knows why. The planet is alive in ways we do not understand. That version travels well. It fits on a thumbnail. It moves through comment sections with the ease of things that feel profound without demanding anything in return. It is not wrong. It is just pointing at the front door of a much stranger building and stopping there. Because what is actually happening in the rocks, in the water, in the instruments, and in the decades of scientific disagreement that have quietly accumulated around this phenomenon is a story about something more unsettling than a planetary heartbeat. It is a story about a signal that should, by now, be explained, and is not. Seismologists first noticed the pulse in 1962. A researcher named Jack Oliver, working with data from a global network of seismographs deployed partly to monitor nuclear tests, identified a recurring microseismic signal with a period of approximately 26 seconds. The instruments were recording it consistently. The signal was not noise. It had structure, it had regularity. It was repeating on a schedule so precise it might as well have been mechanical. Oliver noted it, wrote about it, and the observation sat in the literature. Not forgotten exactly, but not resolved either. No consensus explanation emerged. The phenomenon was real, measurable, and without a clean account of its origin. That is a combination that tends to persist. It persisted for nearly 4 decades. It was not until 2004 that the pulse was pulled back into serious focus. Michael Rie and Barbara Romanowicz at the University of California, Berkeley published a landmark study tracing the signal across the global seismograph network and narrowing its likely origin to a specific region, the Gulf of Guinea off the western coast of Africa. That study appeared in Nature. It changed the terms of the conversation, and it did not close it. That location matters, and it matters in a way the headline version never explains. The Gulf of Guinea sits in the Atlantic Ocean, off the coastlines of countries including Nigeria, Cameroon, Gabon, and Equatorial Guinea. Within it lies a shallow submarine feature called the Bight of Bonny, a semi-enclosed bay where ocean waves interact with seafloor geology in ways that, under the right conditions, can generate seismic energy. The leading hypothesis is that storm-driven ocean waves in this region strike a particular seafloor formation, and the energy of that impact transfers into the solid earth as a repeating seismic signal. That hypothesis, ocean wave interaction with seafloor geology, is not exotic. Microseisms generated by ocean waves are well understood in general. The global seismic background is filled with oceanic noise at periods of 5 to 10 seconds, generated by wave interactions and wave-coast collisions. The ocean and the solid earth are coupled systems, and energy moves between them constantly. That much is not in dispute. The question is whether that general mechanism, applied to this specific location, actually produces this specific signal. And here is where the agreement ends. The Bight of Bonny hypothesis has significant support. The signal's intensity appears to track with storm activity in the Atlantic. The geometry of the seafloor in that region is consistent with the kind of resonance a wave interaction could excite. Multiple research groups using different methods have pointed at the same general area and arrived at compatible conclusions. But consistent pointing is not the same as a closed case. The exact mechanism by which ocean waves translate into a narrow-band seismic signal at precisely 26 seconds, not 22, not 30, not a broad smear of periods, but a remarkably coherent single frequency, has not been fully modeled. Seismologists can describe what conditions would be required to produce it. They cannot yet demonstrate from first principles why this particular patch of seafloor, under these particular wave conditions, locks onto this particular period with such extraordinary regularity. That gap is not a matter of needing slightly better instruments. It is a modeling problem. The physics of how wave energy couples into seismic energy at these frequencies in this geometry remains an area of active research and genuine disagreement. Some researchers argue for a volcanic or hydrothermal contribution. The Gulf of Guinea is geologically active, and the Cameroon volcanic line runs through the region. Others argue the volcanic hypothesis cannot account for the signal's observed response to surface storm patterns. The debate is real. It is ongoing. None of the competing proposals have been experimentally eliminated. A signal that has been continuously recorded for over 60 years, that is detectable on every major continent, that repeats with mechanical precision, and whose source has been narrowed to a region the size of a small country. And yet the mechanism still cannot be fully explained. That is not a gap on the edge of the textbook. That is a gap in the middle of it. Here is where this story asks something of anyone still sitting with it. The 26-second pulse has become, in online science content, a proxy for a certain kind of awe, the idea that the planet is doing something ancient and unknowable that exceeds our understanding. That framing is not entirely accurate, but it is also not entirely wrong. The signal is genuinely unexplained at the mechanistic level. The debate among seismologists is genuine, so here is the question worth placing here, right now, before this continues. Do you think the problem is that we are still missing the right physical model for how ocean energy converts into seismic energy at this scale? Or do you think the deeper issue is that we systematically underestimate how much of Earth's behavior at these frequencies simply has no explanation yet, and we rarely admit it? Leave your answer in the comments. The split on that question tends to be sharper than people expect going in, because what comes next is not about one signal anymore. It is about what the existence of this signal reveals about the boundary between what science can measure and what it can actually explain. The instruments that detect this pulse are called broadband seismometers, buried in isolated vaults, shielded from surface noise, capable of recording ground motion across a vast range of frequencies. The 26-second signal sits in a frequency band that has historically been among the hardest to study, falling between the slow oscillations of major earthquakes and the higher frequency noise of ordinary ocean activity. It lives in a zone where the tools are good enough to see it clearly, but not yet good enough to fully account for it. That zone has a name too. Seismologists sometimes call the broader background of low-frequency Earth vibration the seismic hum. It is real, it is global, and it is only partially explained. Progress has been made in understanding its various components, but progress in understanding parts of a problem is not the same as solving it. And researchers who work in this frequency range are generally careful about that distinction. Now consider what it means that the 26-second signal is not alone. There is a companion signal at approximately 28 seconds, detected from the same region. The two appear related, possibly generated by slightly different resonance modes of the same seafloor feature, or by two nearby but distinct sources interacting with the same storm energy. The existence of a companion signal does not simplify the explanation. It tightens the constraint. Any mechanism proposed to explain the 26-second pulse must also account for why a 28-second signal exists beside it, and what physical system consistently produces two stable resonance peaks separated by only 2 seconds, in a geological environment that is neither perfectly rigid nor perfectly predictable. The models that currently best fit the observations involve what researchers call infragravity waves, very long ocean waves, with periods of several minutes, generated when storm waves interact in deep water and then travel thousands of kilometers to shallow shelf environments, where they couple with the seafloor. Infragravity waves are real and well documented. Their ability to generate seismic energy is real and documented, but translating that general capability into a precise, locked, 26-second output requires knowing the exact boundary conditions of the Bight of Bonny, its seafloor geometry, sediment composition, and wave approach angles, in a level of detail that simply does not yet exist in the published record. The hypothesis is plausible. It has more observational support than its competitors, and it is incomplete. That incompleteness has a specific shape. It is not the shape of a mystery on the verge of resolution. It is the shape of a problem that keeps requiring more precision than the available data can provide, where each new study confirms the general location, narrows the uncertainty slightly, and then stops short of the full reconstruction that would let a researcher say, here is the storm, here is the wave, here is the seafloor. Here is exactly why 26 seconds and not 25, and not 27. The signal was first noticed in 1962. It is 2026. It is still in that gap. That is not a failure of science. Some problems sit at the intersection of ocean physics, solid earth mechanics, and nonlinear wave dynamics in ways that make them genuinely hard to close. The tools required to close them may not all exist yet. That is not unusual in the history of geophysics, but something about this particular problem resists easy comfort on that point, because the 26-second signal is not obscure. It is not buried in noisy data or hidden in a distant observation. It is one of the most stable, regular, globally detectable signals the Earth produces. It is precise enough that seismologists have used it as a reference point, a known, repeatable source in a field where such things are rare. And yet the complete physical account, the one that reconstructs the period from first principles rather than inferring it from the measurement, does not exist. When a phenomenon is that well characterized and still that unexplained, the gap starts to say something, not just about the phenomenon, but about the limits of the framework being used to study it. The Earth has been producing this signal longer than any instrument has been listening. It was pulsing before Jack Oliver's seismographs caught it in 1962. It was doing it during the 19th century, undetected, unrecorded. It was doing it during the formation of the Atlantic Ocean, against different coastlines, under different storm patterns, in a world where the Bight of Bonny may not have existed in its current form at all. The period may have been different then. The source location may have drifted over geological timescales as seafloor features shifted and sediment layers changed. We do not know. We cannot know. The record begins only where the instruments begin, and that is the part the viral version never reaches. The headline says, "Earth has a heartbeat nobody can explain." What the science actually shows is more specific and stranger. Earth has a seismic signal of extraordinary regularity, generated by an ocean-seafloor interaction in a known region, through a mechanism that is broadly understood in category but cannot yet be reconstructed in full detail, that has been measured for over 6 decades, that sits in the literature of a mature scientific discipline, with the tools and the data and the institutional attention it needs to be solved. And that remains, as of today, unsolved. It has a name. The name is the 26-second microsysm. The name appears in peer-reviewed journals and calibration databases, in the footnotes of papers on ambient seismic noise that move carefully around the edges of the problem without closing it. The name is not the explanation, and the distance between those two things, between what we call a phenomenon and what we actually understand about it, is not closing as fast as the clean version of the story implies. The ground moves every 26 seconds. The instruments record it. The debate continues.